Still talking about quadratics, of course. Going to look at the relationship between the roots and the coefficients of a quadratic. So sum and product of roots, we call it. Remember, every quadratic has two roots. Sometimes they're the same, sometimes they might be imaginary, and sometimes, of course, they're real. We're not actually interested in finding the roots for this, it's more playing with them. Now I can get the relationship by factorising. See, if alpha and beta are the roots, then I know it must factorise to be x minus alpha, x minus beta, but the coefficient of x squared is a, so it must be times a there. If I expand the right hand side out, and I'll divide both sides by a and make it a monic, then we can see that pattern. It's a pattern we know. Because remember, when it is monic and we want to factorise it, we say, what two things multiply together to give the last number? So alpha beta turns out to be the constant, C on A in this case. And the sum of the roots is the negative of the middle one. And so that's the pattern we use. Alpha plus beta will be minus B on A, that's the sum of the two roots. And alpha beta will be C on A, the product of the two roots. So now, going back to this idea, if we're going to form a quadratic whose roots are 2 and negative 3. Now we did this before, we just didn't call it the sum of the roots and the product of the roots. It's still the same idea. I'll go, well hang on, I know that they add together to give negative 1, and I know their product's negative 6, so therefore their quadratic must be x squared plus x, because it's minus the sum, and then minus 6 equals 0. I don't have to worry in this case about multiplying by a constant because it's an equation. So it'll work out nicely, just this one. Of course, if we get ones where they turn out to be surds or irrational, so 2 plus root 5, 2 minus root 5, again I can use that idea because the sum of the roots, the irrational part cancels. And product of the roots, difference of two squares, again we end up with a rational number. So that one will be x squared minus 4x minus 1 equals 0. So that idea we had sort of informally talked about earlier. But now we can do much more fun things. So if alpha and beta are the roots of this particular equation, we'll start with the basic ones, alpha plus beta. Well, it's just remembering minus b on a. So in this one, it'll be 3 on 2. Alpha beta. C on A, minus a half. Alpha squared plus beta squared. Now it's really tempting to say that that's just, alpha plus beta all squared. Unfortunately, that wouldn't be the answer. It's close. It is alpha plus beta all squared, but remember, when we square alpha plus beta, we get twice the product. So I've got to subtract that. In reality, it is just my expansion, but I've just moved the 2ab term to the right-hand side to create the formula. So now that I know that, I can sub in what we found for alpha plus beta and alpha beta, play around with those, and we end up with 13 on 4. Another common one they like to ask is the reciprocal of the roots. So 1 on alpha plus 1 on beta. I'll just treat it like an algebraic fraction. Common denominator, alpha beta, we know what that is. The top of the fraction becomes alpha plus beta, and we know what that is. So I can substitute in what we found earlier, and there's my answer, negative 3. Find the value of m if one root is double the other. So in this case, instead of calling the roots alpha and beta, I'm going to call them alpha and 2 alpha. One root is double the other. Now I should be able to set up some equations here so we can work out m. Over here it tells me alpha is negative 2, so it is still simultaneous equations. In this case I worked out alpha first to substitute over there. M is 2 alpha squared, and we get 8 as our answer. A little bit more involved, this one. 2m minus 1x squared plus 1 minus mx. One root is the reciprocal of the other. So in this case, instead of calling them alpha and beta, I'll call them alpha and 1 over alpha. When you multiply alpha and 1 alpha together, you get 1. So actually I don't need to know what alpha is. If I just look at the product of the roots, alpha times 1 on alpha is 1 on 2m minus 1. Alpha disappears. I don't actually need to play with the sum of the roots for this one. Solving that, we get m is 1 for that one. Okay, so 8h, playing with the sum and product of the roots and their relationship with the coefficients of the actual quadratic equation itself.